Hey everybody, welcome back to Calculus AB, and in this one you're going to learn about something new called integrals. Integrals are pretty commonly known as basically the opposite of derivatives or antiderivatives. So what is an antiderivative? Well, let's say you have a derivative f prime of x. Then the antiderivative of that is just going to be your f of x function, or that should be capital case, but your f of x function. So this is your derivative, f prime of x, and this is going to be your antiderivative, or your f of x. So what are integrals and how are they symbolized in calc? Whenever you see an integral, you'll see this sign. And more often than not, you'll probably see a and b at the top and bottom. There's a good chance that a and b might be replaced by specific numbers, but you'll learn what this means about in just a second. So what does an integral tell you? It tells you the area under the curve. So let's take a quick graphical example of this and explain that. So let's say we have our function f of x is equal to x squared. Now this graph, we're only graphing the part of x squared that's in the first quadrant, so it's going to look just like that. Now, actually, let's take a better example, one that's more easier to understand, considering we have a little limited time. So let's go ahead and draw out this entire graph right here. So if you have a graph like this, and we have function y equals x. Now let's say we want to find out what this area is right here. Now granted, for the sake of simplicity, you can calculate the shaded area using the formula of a triangle, considering it's a straight line. But, maybe you'll have a graph that looks like this. Whoops. Maybe you'll have a graph that looks a little bit like this, and you want to find out the shaded area over here. In this case, you can't use the area of a triangle or a circle or a square or something like that, so it's not as easy. So this example is just to show you the basic idea of an integral. So if you want to find out this area, well, what is that area represented in terms of calculus? This is what we call an integral. It's the area under that specific curve, otherwise known as the antiderivative. Now this also means that the graph right here, this graph y equals x, is a graph of your derivative. So this represents f prime of x. Now taking the integral of, right, because an integral is an antiderivative, taking the integral of f prime of x just gets you your original function, which is f of x. Now let's look at what this is represented, or how it's represented graphically, before talking about algebraically. Graphically, it's just the area under the curve, which means that you have a starting point right here and an ending point right here, and you want to find the area under the curve, or the shaded area between these 2 points. These 2 points are referred to as the bounds of the integral. So this right here is a bound. And how is that represented on the integral? A and b are known as the bounds. So let's say you have some sort of function x. Now what does this mean? Well, this means that you're trying to find the area under the curve of this function from the bounds a to b. And let's treat this as bound a and treat this as bound b. So basically you're setting the two limits to what you want your area to be. And that's the graphically essential idea of what an integral is. Now let's talk a little bit more about algebraically instead. So going into the actual calculus part of integrals. As you saw here, integrals are represented like this. So how do you solve an integral? And I'm sure you guys have gone over this in your calculus class. This is just kind of a way to help you clear up any questions you might have. So how do you solve an integral? Let's use the example we were going to use earlier. Let's say we want to find the area under the curve of the graph x squared. And right here, let's just draw that out. So let's say we want to find this area from some point b to a. Now let's swap those. Let's make this a to b, and let's actually assign some values right here. So let's say this point right here is your coordinate at x equals 2, and this is your coordinate at x equals 0. Okay, so first things first, you need a dx right here. Now why? Because it's with respect to x. It's a derivative with respect to x. So you always have to have that in there. Now, quick side note, let's say when we're going more into calculus BC topics or some more complex AP topics, you might have a function represented in terms of y. What is the integral of y squared? In this case, you need dy instead of dx because it's the derivative with respect to y. So that's what, the derivative with respect to some variable allows you to take the integral of that specific variable. So going into the calculus process of this, well, we're going to use what's most commonly referred to as the power rule. Now, this is basically the opposite of derivatives, right? So in derivatives, if you wanted to take the derivative of a function x to the n, that becomes n times x to the n minus 1. So if you want to integrate a function of x to the n, this becomes x to the n plus 1 divided by n. So you're basically doing the opposite of a derivative, and you guys might not be able to see this as easily as it's represented now, but let's go ahead and talk about this, right? We'll use our function x squared here. So if we want to take the derivative of x squared, right, we'll get 2x. What if we want to take the integral of x squared? Well, using our formula here, we get x cubed, right, 2 plus 1 over 3, which is just 1/3 x cubed. Now, why is this the opposite of a derivative? Well, look at it real quickly. If you take the derivative of this function right here, what do you get? Using the power rule, we're going to get 3x squared, but we have that 1/3 over here. And once you simplify that, you get x squared, right? So that's the basic idea behind the integral. It's the opposite of a derivative. Now, this will make a lot of things easier in the future, especially when it comes to trig stuff. But that's the basic idea of the calculus aspect of an integral. Now, why are these bounds here? Okay, let's talk about that for a quick second. So here's one of the most common things you're going to see in calculus, plus c. Now, right now that doesn't make any sense, so let's just sideline this for a second. But we have some integral here, but we don't know what its bounds are. So if we were to graph this, right, as we did over here, let's make it more clear though, right? If we had this function right here, what area are we looking for, right? I mean, this area can go on forever, right? I could continue to draw this graph forever and forever and continue to find that shaded area forever and forever. So we need bounds, and that's what we're missing. So let's call those bounds from our earlier graph right here. Let's name those bounds as 2 to 0 of x squared. And at the same time, let's do the same thing without bounds. So we're going to take the integral of this function both with and without bounds. Okay, well, using this power rule that we just used over here, we know that the derivative of x, or the integral of x squared, is x cubed over 3. Okay, now you always have to have a plus c over here. And here is why. Let's actually, you know what, before we talk about the plus c, let's go ahead and do this, right? So this becomes x cubed over 3 as well. Now there's no plus c here. And I'm going to explain both of these things simultaneously, so I'll try to make it as less complicated as I can. So why do you need the plus c here? Well, let's say you have your function f of x is equal to x cubed over 3 plus 10. What is the derivative of this function? Well, we already know that the derivative of this term right here is x squared, and the derivative of 10 is going to be 0. So the derivative of this function gets you x squared. But what if we have a function, f of x is equal to x cubed over 3 plus 729? Well, taking the derivative of x cubed over 3 once again gets you x squared. So you realize that why you need a plus c here is because this plus c represents any constant number, so any real number that, that doesn't have a variable attached to it. And why is that? Because the derivative of any constant or any real number by itself is just going to be 0, and that cancels out. So you have to account for that 0 or that plus 0 when you're taking the integral, which is why you have to have a plus c here. Because this c value, You'll learn about it more later on, but the c value can be 10 or it can be 729. At this moment, we don't know what it is. But the thing is that c value represents any possibility of this function, right? The function we're looking for might be x cubed divided by 3 plus 10, or it might be x cubed divided by 3 plus 729. We'll talk about this once again later on, so just keep this plus c in mind. Whenever you don't see any numbers here or any bounds, that's when you add plus c. Now why is that? Let's go back to this integral right here. Okay, what is this? Well, we know, actually I don't need this equal sign. So why are bounds here? Well, this bounds represents the specific area that we want, right? We just discussed why we need bounds when regards to plus c, which means whenever we have bounds, we're going to notate it like this. And what is this telling us? Well, it's basically telling us the area underneath this curve from 2 to 0, which is exactly what we want. And what is this notation, or how is this notation showing that? Well, it's telling us we're taking the area of this function from this bound to this bound. And how do you evaluate this? Well, you just plug it in. So this becomes 2 cubed over 3 minus 0 cubed over 3. So you're going to plug in the upper bound first, upper bound, and then you're going to plug in the lower bound. And you can just plug those in mathematically and solve for this. And what do you get? Well, this becomes 0. So you just have to do this. 2 cubed is 8, and you get 8/3. So in other words, the area under the curve from 0 to 2 of x squared is equal to 8/3. Right? So if you were to be able to actually measure the area of this shaded region right here, that would be 8/3. So hopefully you got a lot of information about integrals in this video. In the next video, we're going to try to make this a little more clear through a handful of examples.